to estimate on-peak load using hourly load profiles when direct meter data isn't available. Firstly, obtain monthly load profiles. Contact the utility company or use industry average load profiles to get estimates of hourly load consumption for the specific time of year and location. Secondly, identify on-peak hours. Determine the hours of the day and days of the week that are considered on-peak by the utility company. These hours may vary by season or time of day. Thirdly, calculate on-peak kilowatt-hour consumption. Multiply the hourly load consumption values during on-peak hours by the number of hours in the on-peak period and sum the results. For example, consider a monthly load profile for January that has hourly readings such as 100 kilowatt-hours, 90 kilowatt-hours, and so on, up to 200 kilowatt-hours. Suppose the on-peak hours are Monday through Friday from 6 a.m. to 9 a.m. and 5 p.m. to 8 p.m. To calculate the on-peak hours consumption, add up the kilowatt-hour values for each on-peak hour. For instance, Monday through Friday, the sum of the kilowatt-hours might be 1200 kilowatt-hours. To estimate the on-peak load, divide the on-peak kilowatt-hour consumption, which is 1200 kilowatt-hours, by the total on-peak hours. If there are 10 hours of on-peak time each day, 5 days a week, there are 50 on-peak hours in total. The on-peak load would then be 1200 kilowatt-hours divided by 50 hours, resulting in an on-peak load of 24 kilowatts. Keep in mind that this method provides an approximation of the on-peak load. The accuracy depends on the reliability of the load profiles used. If the on-peak period varies significantly throughout the year, you may need to develop separate load profiles for each on-peak period. Alternatively, consider using load monitoring devices or smart meters to obtain actual hourly load data for more accurate analysis. Analyzing electrical loads accurately is crucial for efficient energy management. Understanding how energy is consumed during peak times helps in optimizing energy usage and reducing costs. Here's a more detailed explanation of the process, expanding on the steps mentioned earlier. Firstly, obtaining monthly load profiles is essential. Contacting the local utility company is often the best approach. Utility companies frequently have historical data and can provide load profiles that are specific to the region and customer type. These profiles show the typical energy consumption patterns throughout the day for different times of the year. If the utility company cannot provide specific load profiles, industry average load profiles are another option. These profiles are available from various sources, such as industry associations, energy consulting firms, and online databases. While they may not be as precise as utility-specific data, they can still provide a reasonable estimate. Consider factors like the type of building, its occupancy, and the nature of its operations when selecting an appropriate industry average load profile. Secondly, identifying on-peak hours accurately is critical. On-peak hours are the times when electricity demand is highest, and utility companies often charge higher rates during these periods. The definition of on-peak hours can vary depending on the utility company, the season, and even the day of the week. Contact the utility company directly to obtain the specific on-peak hours for the location in question. Look for documentation on the utility company's website or contact their customer service department. Typically, on-peak hours are during the daytime when businesses are open and residential energy consumption is also high. Common on-peak hours are mid-morning to early evening, but this can vary significantly. Pay close attention to whether the on-peak hours change during different seasons. Some utilities have different on-peak periods in the summer and winter due to variations in heating and cooling demands. Thirdly, calculating on-peak kilowatt-hour consumption involves a detailed analysis of the load profile. Once you have the hourly load consumption values and the on-peak hours, multiply the load consumption for each on-peak hour by the number of hours in that period. Then sum the results to get the total on-peak kilowatt-hour consumption. For example, if the load profile shows that the energy consumption is 150 kilowatt-hours from 2 p.m. to 3 p.m., and 2 p.m. to 3 p.m. is an on-peak hour, then the on-peak kilowatt-hour consumption for that hour is 150 kilowatt-hours. Repeat this calculation for all on-peak hours in a month and add them together to find the total on-peak kilowatt-hour consumption for the month. Let's consider a more detailed example. Suppose the on-peak hours are from 1 p.m. to 7 p.m. Monday through Friday. The hourly load consumption values for those hours are as follows: Monday 1 p.m. to 2 p.m. 160 kilowatt hours, 2 p.m. to 3 p.m. 180 kilowatt hours, 3 p.m. to 4 p.m. 200 kilowatt hours, 4 p.m. to 5 p.m. 190 kilowatt hours, 5 p.m. to 6 p.m. 210 kilowatt hours, 6 p.m. to 7 p.m. 170 kilowatt hours. To find the total on-peak kilowatt-hour consumption for Monday, add these values together: 160 plus 180 plus 200 plus 190 plus 210 plus 170 equals 1110 kilowatt-hours. Repeat this calculation for Tuesday, Wednesday, Thursday, and Friday. Then add the total on-peak kilowatt-hour consumption for each day of the week to find the total on-peak kilowatt-hour consumption for the week. Multiply the weekly total by the number of weeks in a month to estimate the monthly on-peak kilowatt-hour consumption. Once the on-peak kilowatt-hour consumption is determined, estimating the on-peak load is straightforward. Divide the total on-peak kilowatt-hour consumption by the total number of on-peak hours in the month. This will give you the average on-peak load in kilowatts. For example, if the total on-peak kilowatt-hour consumption for the month is 10,000 kilowatt-hours, and there are 200 on-peak hours in the month, then the average on-peak load is 10,000 kilowatt-hours divided by 200 hours, which equals 50 kilowatts. It is important to note that this is an average value. The actual on-peak load may vary throughout the day and from day to day. However, this estimate can provide a reasonable approximation for load evaluation purposes. The accuracy of this method depends heavily on the quality of the load profiles. If the load profiles are not representative of the actual energy consumption patterns, the estimated on-peak load may be inaccurate. In such cases, consider using more granular data or alternative methods for load evaluation. If the on-peak period varies significantly throughout the year, it is essential to develop separate load profiles for each on-peak period. For example, if the on-peak hours are different in the summer and winter, create a load profile for each season. This will improve the accuracy of the on-peak load estimate. Using load monitoring devices or smart meters can provide even more accurate data. These devices measure energy consumption in real time and can provide hourly or even more frequent data. This data can be used to create highly accurate load profiles and to determine the actual on-peak load. Smart meters are becoming increasingly common and may be available from the utility company. Load monitoring devices can be installed separately and can provide detailed energy consumption data for specific equipment or areas within a building. In addition to estimating the on-peak load, it is also helpful to analyze the off-peak and intermediate peak loads. This can provide a more complete picture of energy consumption patterns and can help identify opportunities for energy savings. Off-peak hours are the times when electricity demand is lowest, and utility companies typically charge low rates during these periods. Intermediate peak hours are the times between on-peak and off-peak hours, and the rates are usually somewhere in between. By analyzing the energy consumption during all three periods, it is possible to identify strategies for shifting energy usage from on-peak to off-peak hours, reducing energy costs. For example, consider scheduling energy-intensive activities, such as running large machinery or charging electric vehicles, during off-peak hours. This can significantly reduce energy costs without impacting operations. Another strategy is to improve the energy efficiency of equipment and buildings. This can reduce energy consumption during all periods, including on-peak hours. Energy-efficient lighting, HVAC systems, and insulation can all help to lower energy consumption and reduce costs. Conducting an energy audit can help identify areas where energy efficiency improvements can be made. An energy audit is a comprehensive assessment of energy consumption patterns and energy efficiency opportunities. It typically involves a detailed inspection of the building, equipment, and operations, as well as an analysis of energy bills. The results of the energy audit can be used to develop a plan for implementing energy efficiency improvements. In summary, estimating on-peak load using hourly load profiles is a valuable tool for energy management. By obtaining monthly load profiles, identifying on-peak hours, and calculating on-peak kilowatt-hour consumption, it is possible to estimate the on-peak load and identify opportunities for energy savings. While this method provides an approximation, it can be a useful starting point for load evaluation. For more accurate results, consider using load monitoring devices or smart meters. Remember that accurate load evaluation is essential for effective energy management. By understanding how energy is consumed during different periods, it is possible to optimize energy usage, reduce costs, and improve the overall energy efficiency of buildings and operations. Moreover, understanding the principles of electrical load management is crucial for electrical engineers, facility managers, and energy consultants. It involves analyzing and controlling the electrical demand of a building or facility to optimize energy consumption, reduce costs, and ensure reliable operation. Here's a more detailed explanation of key concepts and strategies. Firstly, load profiling is the process of analyzing electrical consumption patterns over time. It involves collecting data on the amount of electricity used by a building or facility at different times of the day, week, month, and year. This data is then used to create a load profile, which is a graphical representation of the electrical demand over time. Load profiling is essential for understanding how electricity is being used and for identifying opportunities for energy savings. There are several methods for collecting load profile data. One method is to use smart meters, which automatically record electricity consumption at regular intervals and transmit the data to the utility company. Another method is to use load monitoring devices, which can be installed on individual circuits or pieces of equipment to measure their electricity consumption. Load profile data can be analyzed using various software tools and techniques. These tools can help identify peak demand periods, base load consumption, and unusual or unexpected energy usage patterns. Secondly, peak demand management is the process of reducing the amount of electricity used during peak demand periods. Peak demand is the maximum amount of electricity used by a building or facility at any given time. Reducing peak demand can significantly lower energy costs, as utility companies often charge higher rates for electricity used during peak periods. There are several strategies for peak demand management. One strategy is to shift energy-intensive activities to off-peak hours. For example, a manufacturing facility could schedule production runs during the night or on weekends, when electricity demand is lower. Another strategy is to use energy storage systems, such as batteries or thermal storage, to store energy during off-peak hours and release it during peak hours. A third strategy is to implement demand response programs, which involve reducing electricity consumption in response to signals from the utility company. Demand response programs can be automated, using smart thermostats and other devices to automatically reduce energy consumption during peak periods. Thirdly, power factor correction is the process of improving the power factor of an electrical system. Power factor is a measure of how efficiently electrical power is being used. A low power factor indicates that a significant portion of the electrical power is being wasted. Improving the power factor can reduce energy costs and improve the reliability of the electrical system. There are several methods for power factor correction. One method is to install capacitors which store electrical energy and release it when needed to improve the power factor. Another method is to use power factor correction equipment, which automatically adjusts the power factor to optimize energy efficiency. Fourthly, harmonic mitigation is the process of reducing harmonic distortion in an electrical system. Harmonics are electrical frequencies that are multiples of the fundamental frequency. Harmonic distortion can cause a variety of problems, including overheating of equipment, damage to sensitive electronic devices, and interference with communication systems. There are several methods for harmonic mitigation. One method is to use harmonic filters, which block or reduce the amplitude of harmonic frequencies. Another method is to use harmonic mitigation equipment, which automatically adjusts the electrical system to reduce harmonic distortion. Fifthly, voltage regulation is the process of maintaining a stable voltage level in an electrical system. Voltage fluctuations can cause a variety of problems, including equipment malfunction, data loss, and reduced efficiency. There are several methods for voltage regulation. One method is to use voltage regulators, which automatically adjust the voltage level to maintain a stable output. Another method is to use uninterruptible power supplies UPS, which provide a backup power source in case of a power outage. Sixthly, load shedding is the process of selectively disconnecting non-essential loads from an electrical system during a power outage or other emergency situation. Load shedding can help prevent overloading of the electrical system and ensure that critical loads continue to operate. There are several methods for load shedding. One method is to manually disconnect non-essential loads. Another method is to use automatic load shedding systems, which automatically disconnect non-essential loads based on predefined criteria. Seventhly, energy-efficient design involves incorporating energy-efficient technologies and practices into the design of new buildings and facilities. Energy-efficient design can significantly reduce energy consumption and lower energy costs over the lifetime of the building. There are several strategies for energy-efficient design. One strategy is to use high-performance building materials such as energy-efficient windows, insulation, and roofing. Another strategy is to use energy-efficient lighting systems such as LED lighting and daylighting controls. A third strategy is to use energy-efficient HVAC systems such as high-efficiency chillers and variable frequency drives. Finally, regular maintenance and monitoring are essential for ensuring the continued efficient operation of an electrical system. Regular maintenance can help identify and correct potential problems before they lead to equipment failure or energy waste. Monitoring energy consumption patterns can help identify opportunities for further energy savings. In conclusion, electrical load management is a complex and multifaceted field that requires a deep understanding of electrical systems, energy consumption patterns, and energy-efficient technologies. By implementing the strategies outlined above, it is possible to optimize energy consumption, reduce costs, and ensure the reliable operation of electrical systems. Analyzing electrical loads accurately involves several steps and considerations. Firstly, data collection is paramount. Accurate and reliable data is the foundation of any load analysis. Gather historical data on electricity consumption from utility bills, submeters, and building management systems. The more granular the data, the better. Aim for hourly or even sub-hourly data if possible, especially for critical loads or processes. Secondly, data validation is key. Raw data is rarely perfect. Check for missing values, outliers, and inconsistencies. Clean and validate the data to ensure accuracy. Common techniques include identifying and correcting errors, filling in missing data using interpolation or historical averages, and removing or adjusting outliers that are not representative of typical operation. Thirdly, load profiling is essential. Create load profiles for different time periods such as daily, weekly, monthly, and seasonal. Load profiles visually represent energy consumption patterns and help identify peak demand periods, base load consumption, and variations in energy usage. Use graphs and charts to visualize load profiles and make it easier to identify trends and anomalies. Fourthly, baseline establishment is crucial. Establish a baseline energy consumption level based on historical data. This baseline serves as a benchmark against which to compare current and future energy performance. Consider factors that may influence energy consumption, such as weather conditions, occupancy levels, and production schedules. Fifthly, peak demand analysis is vital. Identify peak demand periods and analyze the factors that contribute to them. Peak demand often drives a significant portion of electricity costs, so reducing peak demand can lead to substantial savings. Look for opportunities to shift or reduce peak demand, such as scheduling energy-intensive activities during off-peak hours or implementing demand response strategies. Sixthly, end-use analysis is important. Break down total energy consumption into end uses such as lighting, HVAC, equipment, and processes. This helps identify which areas consume the most energy and where efficiency improvements can have the greatest impact. Use submeters to measure energy consumption for specific end uses and identify energy hogs. Seventhly, correlation analysis is useful. Explore correlations between energy consumption and various factors such as weather, occupancy, production levels, and operating schedules. This helps understand the drivers of energy consumption and identify opportunities to optimize energy use based on these factors. Use regression analysis or other statistical techniques to quantify the relationship between energy consumption and influencing factors. Eighthly, benchmarking is valuable. Compare energy consumption to industry benchmarks or best practices. This helps assess energy performance relative to similar facilities or operations and identify areas where improvement is needed. Use energy benchmarking tools and databases to compare energy performance and identify potential savings opportunities. Ninthly, energy audit integration is recommended. Integrate data from energy audits into the load analysis to identify specific energy efficiency opportunities. Energy audits provide detailed assessments of energy-consuming systems and equipment and identify potential improvement. Combine audit findings with load analysis data to prioritize energy efficiency projects based on their potential impact and cost-effectiveness. Tenthly, modeling and simulation can be beneficial. Use energy modeling and simulation tools to evaluate different energy efficiency scenarios and predict their impact on energy consumption. This helps optimize energy efficiency strategies and make informed decisions about investments in energy-saving technologies. Use building energy modeling software to simulate energy performance under different conditions and evaluate the cost-effectiveness of various energy efficiency measures. 11thly, reporting and communication are essential. Communicate the results of the load analysis to stakeholders, including facility managers, building owners, and occupants. Present findings in a clear and concise manner and highlight opportunities for energy savings. Use reports, presentations, and visualizations to communicate key findings and recommendations. Finally, continuous monitoring and improvement are crucial. Implement a system for continuous monitoring of energy consumption and tracking the performance of energy efficiency measures. Regularly review load analysis data and identify new opportunities for improvement. Use data-driven insights to continuously optimize energy use and reduce energy costs. Accurately analyzing electrical loads involves a combination of data collection, data validation, load profiling, baseline establishment, peak demand analysis, end-use analysis, correlation analysis, benchmarking, energy audit integration, modeling and simulation, reporting and communication, and continuous monitoring and improvement. By following these steps, it is possible to gain a deep understanding of energy consumption patterns and identify opportunities to optimize energy use, reduce costs, and improve energy efficiency.